Every piece of ordinary matter in the universe is composed of atoms, so small that a single strand of human hair is 150,000 carbon atoms wide. If these atoms were the size of an average human cell, which is still unbelievably small in size, the smallest amoeba would still be around 1.18 meters, or around the length of a golf club. Atoms are officially defined as the smallest units of matter that exhibit properties of chemical elements, and the 118 known elements are listed in the marvelous diagram known as the periodic table. Atoms are not loners, though. Together with other atoms, they form the basis for molecules, which can be unfathomably microscopic or bizarrely gargantuan. Atoms are the sole reason every piece of matter in the universe can exist, including humans, the device you're using to watch this video on, the Earth, the Sun, and a lot of other objects. Without atoms, most, if not all, of the universe could not exist. But how do they form molecules, and what else are atoms capable of? Atomic Structure 101. Atoms are often described as the smallest unit of matter. The word atom originates from the Greek word atomos, which is defined as uncuttable or unsplittable. The fallacy that atoms are the final layer of reality persisted until the 1900s. The 20th century heralded a mass cultivation of the composition of the atom. In 1906, the chemist J.J. Thomson was discovered that atoms had electrons, negatively charged particles, inside of them. Ernest Rutherford revised this model as having a densely packed positively charged center, with a small number of electrons orbiting the nucleus. Niels Bohr revamped this theory by adding energy levels that the electrons orbited on. Quantum physics spotted a lot of holes in his theory, but as of this video, the Bohr model is still a good representation of the atom. Throughout the evolution of the atomic theory, we have found that three particles make up the atom. The electron is the microscopic particle that whizzes around the center of the nucleus, that carries a negative charge. The proton is a larger particle that sits in the center of the nucleus, with the neutron, which has a neutral charge. Let us assume that each electron energy level resembles the structure of the solar system, and that the electrons orbit around the central nucleus, the same way that the planets and minor bodies orbit the central sun. Each energy level can only hold a fixed amount of electrons. There is a maximum number because electrons all contain a negative charge, and the concept of like charges, such as electrons, repelling is fundamental to the roots of electromagnetism. For now, assume that electrons are trying to maximize the distance between themselves. However, there is limited amount of space that a single electron orbital can supply to the electrons, so eventually the shell will be filled. The closer shells have a maximum capacity that is smaller than the outer shells. More specifically, each electron shell can carry a maximum of 2 n² electrons, with n being the nth shell. However, you can imagine the electrons further away from the nucleus are more unstable and loose. Thus, all electrons tend to fill out the lower shells first before moving upwards. The outermost electron shell is known as the valence shell. Depending on the element, the electrons in the valence shell, called the valence electrons, also vary in numbers, except for the noble gases. All atoms have to complete their not full valence shell because of the octet rule. This forms the basis for atomic bonds, ionic bonds. The first type of bond we will immerse ourselves in is the ionic bond. Ions are what chemists refer to as charged atoms. All atoms in the periodic table are electrically neutral because the number of protons and electrons in the atom are equal. Atoms that lose or gain electrons are called ions. Atoms that lose electrons and become positive are known as cations, while atoms that gain electrons and become negative are known as anions. If an atom with few electrons in its valence shell comes close to an atom with many electrons in its valence shell, the first atom will donate electrons, and the two atoms will go to a redox reaction. The first atom will become a cation, while the second will become an anion, and the two will attract each other. In an ionic bond, for example, sodium chloride, table salt, Covalent bonds are another fascinating type of bond. Instead of completely donating and completely taking electrons like ionic bonds do, atoms participating in covalent bonds share electrons. Covalent bonds occur between two nonmetals. For example, two hydrogen atoms covalently bonded to an oxygen atom forms the molecule water. However, oftentimes the sharing is not equal. Sometimes some atoms are more attractive than other atoms, and thus the electrons tend to orbit around a stronger atom. This quality is known as electronegativity and forms the basis for intermolecular forces. The slight attraction and slight repulsion can cause a positive or negative charge in a part of the molecule, written as delta plus and delta minus, respectively. Metallic bonds. Metallic bonding occurs only in metals or metallic alloys. The valence electrons of atoms participating in metallic bonds are delocalized, meaning that they can move around from atom to atom. This forms a sea of electrons, and the abandoned atomic nuclei are left with a positive charge. This constant flow of electrons forms electrical conductivity. Conclusion. There are three types of atomic bonds, or intramolecular forces: ionic, covalent, and metallic. Each of them results in the construction of molecules and eventually entire substances. You, your computer, your car, your house, and the entire universe can only exist because of these bonding atoms. Thank you for watching this video of the Information Institute. Please subscribe to our channel.